Hello everyone. Today I would like to go over the topic of unit cells with you guys. What unit cells are, what they're made of, what they can make up, and I want to define for you guys what atomic packing factor is. And we're going to get to that later in this presentation, but before we did, first I want to introduce you guys to Arthur Atlas. Arthur, he's just your ordinary guy. He's got a wife, he's got some children, he's got a really nice house. Kind of the perfect life, quote unquote. Until, unfortunately, one day when he was driving on a very snowy road in a very nice car, he was driving behind a truck that was carrying some radioactive waste. And because it was snowy and it was a blizzard out that day, he lost control of the wheel and he crashed into the truck, causing all of the radioactive material to pour out onto him. Luckily, Arthur survived the accident, but he noticed he was kind of changing. During the healing process, he began to notice that he can kind of change the objects around him. And what I mean by changing the objects around him is that he can kind of change the material properties, change the strength of the objects around him. So he noticed he could turn a very, very strong material with just the wave of his hand into a very weak and fragile material that can be broken by just the tap of a finger. So Arthur realized that from this accident, he developed these superpowers. And what better way to use these superpowers than to become a superhero? So that's when Arthur decided to become more than just a person, but to become the unit cell. Now, since I stated earlier, the unit cell has the ability to change a material's atomic structure, and that's really what unit cells are. But I'm going to talk about that in a little further. So you can really change material properties. So take, for example, when he goes up against this ninja. This ninja, fierce and scary looking, is carrying a very strong sword in front of him, wielding it at Arthur. Arthur, with just the wave of his hand, can change this very, very tough and durable metal into something so fragile and so brittle that even the smallest wind breezing by can turn it into dust. And that's really the true power of the unit cell. He can change the atomic structure and the atomic layout of any material. So with this, Arthur decided, you know what? Why limit myself to just fighting these petty little ninjas when I can fight bigger and stronger villains? Which is when he decided to team up with better superheroes. So now these guys are going to take on some, they can really do some damage. So that was just a brief introduction of Arthur and the unit cell. And now that we kind of know how the unit cell works and what his powers are, I want to describe to you how he actually works. In order to do that, we kind of have to first start out with, what exactly is a unit cell? So a unit cell is kind of the structure of material. It's the way the atoms are arranged, and that arrangement is called the unit cell. If you want to look at it this way, it can kind of be considered the box that houses the atoms. And when the unit cells are arranged next to each other in a pattern, they form this kind of 3D structure, and that's really what the materials around us are. They're just 3D structures of these atoms. Take, for example, this wallpaper. If we were to say, look at the wallpaper individually and look at the kind of pattern that makes up the wallpaper. There's these kind of, circular, diamond-y shaped structures with a turkey-looking tree in the middle. I really don't know what that is, but, it's a nice-looking wallpaper. But these structures kind of repeat themselves, in a 2D dimension. And after a while, they kind of form the whole wallpaper. And that's the same in the unit cells. Consider the unit cell as this individual diamond, and it just repeats itself on and upwards, downwards, sideways, in all three directions, making a 3D dimensional object. And when they repeat themselves, they kind of form the unit cells. And that's really what a unit cell is. It's just the way the atoms are arranged and how they're structured. So that's really what a unit cell is. Now that we kind of know what it is, let's dive into a little bit more about what we'll be covering today. So I want to go over with you guys 3 different cubic structures of unit cells. We have simple cubic, body-centered cubic, and face-centered cubic. Now, as I stated earlier, unit cells repeat themselves in 3D dimensions to kind of form structures. So if we look at this object, this picture to the right, we can see if this shaded in box is a unit cell, it repeats itself, and they kind of form this whole matrix or this bigger box of these atoms, and that's what really forms the materials around us. But they don't really, I guess you can consider each unit cell kind of shares the adjacent atoms with it, but a better way to look at it is that each unit cell is kind of, it only owns, I guess, a piece of the atom. So look at this picture next to it. Let's say this first box that, in this corner is a unit cell. We can kind of see that it only really owns a piece of the atom. But when it's put next to these other three and then these four beneath it, it forms an entire atom. And although, it's not really a piece of an atom, being kind of glued together to another piece, it's just the way they're arranged. This is the way we look at it. When atoms are arranged in a certain way, we kind of, put them into this kind of box-like structure and call it a unit cell. And that's really how unit cells are, oriented. So if we look at simple cubic, we can see that it's made of an eighth of an atom at each corner. So for this structure, we can tell that this is an eighth of an atom. So imagine, like this picture, we have an eighth of an atom at each corner, and if it has 8 corners, that means an entire simple cubic unit cell is composed of one atom. Moving on to body-centered cubic, more or less very, very similar. It's also composed of 1/8 of an atom at each corner, but it has one atom at its center. So if we add up all the atoms, we have one atom at its center. We have 8 1/8 atoms at each corner, so adding, simply, we get 2 atoms. Lastly, for face-centered cubic, we have an eighth of an atom in each corner, and then we have 6 half atoms at each face. So 6 half atoms would really be 3 atoms, plus the 1/8 atoms at 8 corners, which gives us a total of 4 atoms. So this is kind of how many atoms are in each unit cell, and this kind of leads us into our next topic, which is the atomic packing factor. The atomic packing factor, or APF, really just states how many atoms are kind of squished into each unit cell. And think of ball pits at like McDonald's or Chuck E. Cheese's when you guys played in those as kids. I always wondered whenever I played in those ball pits, how many balls are actually in this thing? And I thought, as a little kid, I was like, oh, there's probably like 1,000 or, 1,000,000 balls in this ball pit. In reality, it's probably like, a couple hundred. But my point is that I wondered how many balls they could fit in the ball pit. That's really what I wondered. And that's what the atomic packing factor is saying. So the APF of a ball pit would really just be saying how many balls, percentage-wise, are squished into this ball pit. And that's exactly what it is for the unit cell too. It's really saying how many atoms are inside this structure. But of course, it's not just one atom. For example, body-centered and face-centered cubic have 2 and 4 atoms. So we multiply the number of atoms by the volume of the atom, and then we divide that by the volume of the structure. So because we're working with only cubes today, simply the volume of the structure will just be its side length, which is A cubed, just A cubed. And the volume of this atom, which we can represent as a sphere, is 4/3 pi r cubed. Now the only tricky part about actually finding the atomic packing factor is finding a relationship between A and R. And I'll get more into that in our next few slides. I'm going to teach you guys how to solve for the atomic packing factor for simple cubic, body-centered cubic, and face-centered cubic. So yeah, let's get into that right now. So now that we know what an APF is, what an atomic packing factor is, let's actually solve for them. So we said that earlier, this side length of a cube was A. And before I continue further with this, I just want to say I'm kind of new to writing with this pen stylus, so if my writing's a little sloppy, please, I'm sorry. But anyway, continuing. So we know the side length is A, and the radius of the sphere kind of stretches from here to here. So let's label that the radius, and then the radius of this sphere, this atom, kind of stretches from this corner to this corner. Label that R. And immediately we can kind of see that because the radiuses are touching, like the radius extends immediately, and then following that, the radius extends back to this side, we can kind of tell that one side length, A, is kind of equal to 2R. And like I said, the toughest part of solving for APF was developing a relationship between A and R, and we just did it real simply. So now that we have this relationship, let's plug it back in. So we know that the number of atoms for simple cubic, this is a simple cubic structure by the way, I'm sorry if I forgot to mention that earlier, is we have 1 atom times, we have 4/3, and then pi r cubed and all over, I'm just going to put 2r cubed. Alright, and now all that's left to do is actually solve this. So, 1 times 4 is still just 4. So we still have 4 thirds pi r cubed on top. And on the bottom, we have 2 cubed, which is 8, times r cubed, which is simply r cubed. And we immediately see that these r cubes cancel each other out. So all that we're left with is 4 thirds pi on top over 8. And if we plug that into our calculator, we get a value of approximately 0.5236. Sorry for my little sloppy 3. Keep in mind this is percent, so we always multiply by 100. So multiplying by 100, we're left with about 52. I'm going to round up here, 4%. And what this is saying is that 52.4% of this atomic structure, of this unit cell, of this simple cubic unit cell, is filled with atoms. And that's really all the atomic packing factor is saying, how percentage-wise, how much of the atoms take up the space in a unit cell. So that's it. Now that we solved for simple cubic, let's move on to some other ones. Let's go on to face-centered cubic. So again, we have, let me just get my writing tool. So we have, again, a side length A. This one's going to be a little trickier, but if we work through this together, if we look from this corner to this corner, we can let's just draw a line straight diagonal-wise down. We can kind of see that, this radius plus this diameter of this atom plus this radius equals the length of this hypotenuse, of this face. So let's just label this hypotenuse x, and we can up here say that x is equal to, we have one radius plus a diameter, which is 2 radiuses, plus another radius is equal to 4 times r. And then we also know that if the side length is a, this side length is also a. So now we kind of have, if we notice, we have a triangle. Not just any triangle, poorly drawn triangle, but a right triangle, nonetheless. And we can use the Pythagorean theorem to solve for the relationship between a and x. So we know that, the Pythagorean theorem, a squared plus b squared is c squared being the hypotenuse. So in this case, we can say a squared plus another a squared equals x squared, which is really just 4r squared, and 4 squared is 16. So I'm going to skip a step and say 16r squared. Now let's just add these together. We have 2a squared equals 16r squared. Let's divide by 2. So we have a squared equals 8 times r squared. And finally, take the square root to give us a equals the square root of 8r. And that's it. That's our relationship between a and r. So now let's plug that back into the atomic packing factor equation. So if you recall, the number of atoms in a face-centered cubic is 4. So we have 4 times, get a big bracket going on, we have 4 thirds pi r cubed all over a cubed, which is really, let's get parentheses, root 8 times r cubed, and that equals, now we have 4 times 4 is 16, so we have 16 over 3 times pi over the square root of 8 cubed is, I'm just going to simply put it as the square root of 8 times r cubed. And I'm so sorry, I forgot to include my r cubed up here. But we can already see that, these r cubes are going to cancel. So what this really equals is 16 over 3 times pi. Nope, silly me. I said cubed it, but I forgot to write in cubed. Over the square root of 8 cubed, which is really just 2 root 2. But you know what? We can plug it into our calculator as the square root of 8 cubed. It doesn't really make a difference the way we plug in, and as long as we plug in correctly. And this is going to give us a value of about 0.7405, and don't forget percent, so we gotta multiply by 100, so about 74%. So we can see that comparing this to simple cubic structure, which is about 52%, this is much, much more densely packed. So this is a lot stronger, it's more densely packed than the simple cubic, and because it's more densely packed, we can kind of figure out that it's just going to be harder to move around. It's going to be harder to deform. So just think, trying to, if you had an empty, kind of very easily deformable cube in your hand filled with, 52.3% of spherical balls, moving it around is going to be difficult, but it's going to be fairly easy. But now can you imagine if it's 74% filled? It's going to be a lot tougher to kind of squish together, just because these balls are kind of repelling against each other. And that's really what it's saying. So now we know that, the face-centered cubic is very densely packed. It's going to be a lot stronger. So going back to the unit cell and his powers, if he took something that was face-centered cubic structure, which is 74%, which is fairly tough, and then he changed it into, let's just say, for our sake, a simple cubic, it's a lot weaker. It's going to be a lot easier to break. Now moving on, lastly, we are going to solve for the atomic packing factor of a body-centered cubic. Now, I want you guys to pay attention for this one because it's the hardest one to solve for. It's a little tricky. So we know this is a side length A, correct? And we also let's just look at this corner, this top right corner, and this bottom left back corner. We can kind of see that if we were to draw a line straight through connecting, let's just label this X, we can kind of see that this radius plus this diameter plus this radius equals the length. So, like I said, we have a radius plus a diameter, which is just 2 radiuses, plus another radius is that length, which is 4r. So now we have a good way to measure r, but we still need a way to tie it to a. Well, we know that this length is a, and we know that this length from this corner to this corner, just like FCC. Remember how we solved for using the Pythagorean theorem? We're going to have to use it again in order to solve for this little hypotenuse. But we can see that this kind of makes a right triangle going into it. So if we label this A, let's label this hypotenuse Y, and this is another side length A. So let's find a relationship, really simple, using Pythagorean theorem between Y. We did this last time. I'm going to skip a few steps. So the 2a squareds added together, so you got 2a squared is equal to y squared. So if we just take the square root of this, we have the square root of 2 times a equals y. So now we have a relationship between a and this, this hypotenuse length y, and now we can use the Pythagorean theorem again to solve for this relationship between a and r. So solving for it again, we have a squared. Remember, I'm doing this bigger triangle now. So let's just draw a dotted line to separate. We have a squared plus, y squared, which is 2a squared, equals 4r squared, which again is just 16r squared. So now adding, we have 3a squared equals 16r squared. Just because I'm running out of room, I'm going to skip a step or two. I'm just going to divide by 3. and take the square root. So A is equal to the square root of 16, sorry for the small handwriting, over 3 times R. Great, now we have a relationship. Let's solve for the APF. So, for body-centered cubic, we're going to have 2 atoms times 4/3 pi r cubed all over a cubed, which is just this relationship down here. So let's put that in brackets. The square root of 16 over 3 times r cubed. And I'm gonna, bring the 2 in. So we have 2 times 4, which is 8/3 pi r cubed over, I'm just going to leave that square root of 16/3 cubed as is, times r cubed. And we can see as before, the r cubes cancel. And what we're left with 8/3 times pi divided by the square root of 16 all over 3 cubed. And plugging that into your calculator, we get about 0.68. Keep in mind percents, so it equals about, after multiplying by 100, it's going to be about 68%. So this is saying is that 68% of a body-centered cubic structure is filled with atoms. So just comparing, we know that face-centered cubic was about 74%, which is the most densely packed. So yeah, I hope this video was a little helpful for you guys, for those who are figuring out how to solve for the APFs and kind of what a unit cell is. Yeah, I just hope you guys found this video a little bit useful, and thanks for watching.